All right. So Calculus 30 class today is 11.3 in your textbook, the Substitution Rule. We've been talking about integration, about integrals, and we've been connecting definite integrals, right, with antiderivatives, evaluated at the limits of the integration, and then taking the difference there, right? So that's how you find, let's say, an area under a curve. It's called a definite integral, the evaluation of a definite integral. An indefinite integral would be a function. It would be a description, a mathematical relation describing how you would find the area under a curve or other things that integrals represent. But it's just a general equation. That's why we had the plus c. Okay? So we've talked about definite, indefinite integrals. The problem is, in our previous work, and if I just kind of zip back here, in our previous work, this looks pretty complicated, all right? But we found out last day that we actually could rewrite this in a way that's not that complicated, right? By bringing this term up to the numerator there. And here we have a fairly simple sort of polynomial, a binomial function. And so to take the individual antiderivative of each of these and form that as our integral, not a big deal. The big deal comes when we have functions that we can't just simply rewrite into a nice friendly way for us to find the antiderivative. And this one is not going to be that tough, the one I'm going to start with, but I think you'll find that it does look a little bit different. So if we have, take the integral of x minus 2 to the power of 4 dx, okay? So here's our function, x minus 2 to the power of 4. Now right away you see that we have a binomial and it's taken to another power. If we expanded this, we would get this polynomial, long polynomial term. But expanding this, I don't really want to do that. That takes a lot of effort, actually, right? I mean, not if you know the binomial theorem, which I don't know if you guys remember from pre-calculus 30. The expansion of the binomial a plus b to the ultimate power of n. There was a format you could follow. Anyways, that still takes a lot of time. So why would we do that? We know that there's shortcuts to differentiation, okay? And if we were differentiating something that looked like this, then what rule would we have to use? There's two rules really we would have to keep in mind. What rules? What are the shortcut rules for differentiating? Just that I've circled in yellow. What rules are they? A little bit of a test. We're coming to the end of the semester here. What do we got? Chain rule and what's the other one? Kind of what's the first thing you would do to this? Take the derivative. You would bring that power down as a coefficient. Power rule. Okay. So power rule, chain rule. Yes. Very good. Now, if we have two functions or two parts to this, and of course we have the outside function, which would be maybe u to the 4th, and we have an inside function, which would be maybe x minus 2, right? There's the outside, there's the inside. Two parts, chain rule. The substitution rule in calculus helps us to undo the chain rule. Okay? And again, this is a very simple example to do. Okay? I want to show you something over here. What we do, first of all, is you would try and find out what the inner function is. You would identify the inner function, in this case, to be x minus 2. And so you'd let that equal to u. U equals x minus 2. Okay? Now, it's going to be important for us to identify what du is, or the derivative of u. Okay? And so the derivative of u with respect to x is what? What's the derivative of this? 1, right? Derivative of x is 1. Derivative of negative 2 is 0. So 1 minus 0. Okay? So the derivative is 1. Now, we haven't spent a lot of time on this in the Calculus 30. We haven't spent a lot of time on differential equations. Okay? But when we're talking about differential equations, we can write an equation that sort of represents, that has different derivatives of different things in one equation. So we're talking about, when we've done implicit differentiation, it's sort of, what we've had. We've had, y prime, x, and y double prime, y prime. Okay, so different derivatives and that sort of thing. This is not really a ratio in a sense that this is a dividing sign, right? We know that. In calculus, this is not du, some quantity divided by another one. But in some sort of way, we can view this as a bit of a ratio. And we can say that, hey, the derivative of u is actually 1 times the derivative of x. And this is sort of what we call like a differential equation. So it's kind of like you can manipulate it in the same way by multiplying both sides by dx, okay? So, like I say, I want to just qualify this just briefly by saying this is not a division, but in calculus we can treat it the same way. So, what this is saying is that du actually equals dx. And right now, if we could write this whole thing right here, actually the whole thing, but if we can write this part and this part, rewrite it in terms of something really simple that we can take the antiderivative of, that's going to help us. And so watch what we're going to do. We're going to write this as the integral of u to the 4th. And we're going to make, because dx actually equals du, look at, we can write this is u to the 4th after we've substituted, hence the fancy name substitution, okay? And we've actually determined that dx here is actually equal to du, okay? Which makes sense because the derivative of x is 1 here, all right? The antiderivative of 1 is x, good, okay? So that is a huge, big first step right there, substitution. It's also called U Substitution. Okay? You'll see this in university courses and online videos and all this sort of stuff that you look up. U Substitution, because we're substituting some kind of expression for a single variable u, and u is the one that's often used. All right, now can we find the antiderivative of this? Hey, much easier than this. No chain rule involved, just power rule now. Okay, so the antiderivative would be 1/5 u to the 5. Boom, right? Because really, now if we're doing plus c, if we're doing indefinite, which we probably will here, we're not quite done yet, but let me show you this. Remember that this part and this part, they kind of go together, right? So when you take the antiderivative, this and this goes. But you have to make sure that this is u and this is u, right? It can't be u here and x here. That's not good. Not good at all. And finally, now we unsubstitute, really, and we know that u is actually equal to x minus 2, and so we have actually 1/5 x minus 2 to the power of 5 plus c. And that would be our answer. Okay? I liken this to in pre-calculus, okay? Let's say you have a difference of squares where the perfect square in that difference of squares is actually another polynomial. You can substitute, that polynomial, right? So on a little somewhat related note here, if you had x plus 2 squared minus 9, and I asked you to factor that, and you go, okay, okay, maybe I'll expand this and make a trinomial here, and then, oh boy, what do I do? You can look at this and say, hey, I see this as a difference of squares. Perfect square, difference. Let's let, right, x plus 2 equal u, and you have u squared minus 9. Hey, no problem. U plus 3, u minus 3, substitute this back in for u. We did that, right? That's what we've done because it makes taking the difference of squares a lot easier. You don't have this big polynomial stuck in there. That's in essence what we're doing. Now, this is a simple example, okay? What happens if we have okay, let me do the next example, okay, and you'll see where we have to adjust just a little bit, okay? So write this down. Here's our next example in white here. We have 3x minus 2. Very similar to the one we just did, okay? Very similar to the one we just did, but this is a little more complicated. Why? Because we don't just have x in this sort of inner looking function. Don't just have x, we have 3. Oh my goodness. When you take the derivative of 3x minus 2, you have to multiply by 3. Now, it is kind of handy we have this out here, okay? And I want you to notice that, all right? What I want you to notice is when you're choosing u, okay, it's good to look at what would be the inner function. But it's also really handy to be able to identify the derivative of that inner function as well. If that is in there, then you know for sure that that is the u you're looking for. Okay? So here is an inner looking function, and here is the derivative of that inner looking function. So that's the clincher. U equals 3x minus 2. That's what we're going to substitute u for, is the 3x minus 2. Okay?